Hello and thank you for joining us on our continued educational journey through surface preparation. My name is Kevin Hawthorne, and as always, I'm joined by our resident subject matter expert, industry patriarch, and substrate technology president, Josh Jones. Josh, give us a brief explanation as to what causes imperfections such as cracks, unwanted expansion, and spalling.
Yeah, sure. I'd be happy to. Cracks can take place because of shrinkage after placement of the concrete slab. Basically, it indicates any kind of movement in a structurally rigid slab. So if there's any kind of movement, what the cracks are indicating is that movement was great enough to break that rigid material apart. Again, it could be during the placement, after it's placed, and the shrinkage that takes place could actually pull it apart to some extent. Or there could be movement after the slab was installed, whether it's because the sub base had moved. Nobody really knows, but it just indicates that there was movement in that slab that it just couldn't handle without cracking or breaking apart at that point. With regard to spalling, the spalling is basically going to be any kind of damage that was incurred, maybe nails that were placed in the floor, or any kind of fixtures that were installed to the concrete slab that when it was time to renovate, those pieces or those nails or lag bolts, whatever it be, was yanked out of the slab, and of course the concrete broke away with it, so it leaves a spall. The only other way that a spall would happen other than abuse from fork trucks and things like that could possibly be during placement, where parts of this slab with bleed water and the way that it was placed left hollow spots in the surface of the slab. But again, the voids, how they took place, are not really as important to understand as much as noticing them and realizing the repair that has to take place in order to make them smooth again with the adjacent areas of the slab around them.
So from a contractor's perspective, there isn't one identifying cause. It could be a variation of many causes or a combination. There really isn't a way for a contractor to come in and identify the problem, what causes the joints or the cracks. His job is just to come in and fix them.
Correct. I would say that the biggest word of caution for a contractor that is assigned to come up with a solution for a crack or a joint that has to be filled would be that they're competent enough to assess that joint or crack should be filled or can be filled. Because there is no way to guarantee future movement can be stopped, or that the slab may choose at some point, whether it's thermal expansion and contraction, whether it's sub-base integrity that's in question. It's very difficult to know those things. So I think the biggest word of caution for a contractor would be to assess the items that need to be repaired, but also that there's actually going to be a fix for that will provide a repair that lasts. Future movement that could cause anything to fail, of course, the contractor could be responsible for that. So the biggest word of caution is to make sure that whatever movement has taken place, we can reasonably predict that it won't occur again. But again, there's no guarantee. If the slab wants to move to the extent that's greater than the repair's strength, then it will move and it will crack.
Okay, so let's get into specifics. Cracks. What is a mechanical preparation that you as an industry expert would do to prepare a crack to fix it?
Well, when you consider the nature of the crack in the slab, whether it's from movement or from shrinkage, whatever it might be, we can expect that as that rigid material moved and the crack is the indication that it moved, it's reasonable to assume that the crack is probably not only where we see the opening in the concrete. In other words, the force that pulled slab apart at that point probably didn't break along a perfect line. So that means not only is the crack obviously the portion of the floor that has to be filled, but also the sidewalls of that crack where the concrete literally ripped itself apart. There's going to be cracking there that probably can't even be seen. I mean, certainly there could be analysis done, there could be core samples taken, but that's way more than most projects are going to justify in terms of expense and time. So if we assume that the crack took place because there was movement in a rigid material, then it's safe to assume that the sidewalls of that crack or cracks are going to be also micro-cracked. From a surface preparation standpoint, the first thing that I'm going to try to fix is going to be getting rid of anything that's structurally unsound. So if we assume that those sidewalls have micro cracks, and that material has to go as well. I don't know that there's really a formula for it, but when it comes to the crack itself, we need to make sure that the vertical walls of the crack are clean so that the coating can stick. But at the same time we're doing that, our intention is to remove some of the sidewall material that, again, contains micro cracks that we can expect are there, though we can't see them. So if I have a crack that, let's say, is 1/8 of an inch, as an example, I would probably want to widen it out at least to a quarter of an inch, maybe even more. It just depends. It depends on how wide the crack is. It depends also on the equipment that's being used too, because cracks don't usually take place in a perfectly straight line. A saw blade is a perfectly straight tool. So if I want to cut a crack to not only open it up and remove the micro cracking that we expect to be there, there's a good chance that that saw blade is going to have to navigate that angled shape of the crack, because the crack doesn't run in a straight line. So what we end up with is a crack that probably is going to be a little wider. The cuts might be a little further out than we anticipate. But if we're trying to chase those sidewalls and get rid of all those micro cracks, then we might end up with something that looks like kind of a nasty cut in the concrete. But our objective, again, is to prepare the sidewalls of the crack and also get rid of any of the microfracturing that, again, can reasonably be expected to exist.
Okay. Good. Paul, first, welcome to the show. Paul joins us from Smith Paint's manufacturing facility in Hershey, Pennsylvania. So, Paul, based on Josh's analysis of how to mechanically prepare, how would you chemically then come behind him, and what products do you have or does the industry have that would repair that joint?
Well, you really run into a couple different scenarios. So you have thinner cracks where you're trying to repair something that would, let's say, be more along the lines of less than a quarter of an inch wide, to larger repairs, which are going to require a thicker consistency material. Possibly, if you're at an angle, you want something that isn't going to be as fluid as something that needs to soak down into a fine crack. So you're looking at, for a fine repair where you're just chasing a crack open to clean it out and have a nice, sound, and solid wall to bond to, you're looking at a much lower viscosity liquid material that can soak in, and you'll never fully get all of those little micro cracks out, but you need something that can navigate those in a clean void and kind of think of it like a root structure where it soaks into those little pores, holes, and cavities, and then stitches it to both sides and anchors it properly to the concrete. So that would be something along the lines of a low viscosity repair material like a urethane or an epoxy that's typically designed for repairing like bridge decks or some sort of suspended concrete decking system where it can soak in and fuse back together relatively quickly, but also attain outstanding adhesion that's greater than the concrete itself. In most cases, if you're getting any thicker than literally human hair, you're going to utilize some sort of filler like a sand or something like that to help it bulk up. One, from a cost standpoint. Two, because the material's so liquid, you don't want it so fluid that it just disappears when you put it in the hole. Especially if you cut an 1/8 inch crack, now a quarter inch wide, most of it's going to disappear. So you need something to help bind it there because it's meant to soak in, just like it is to the concrete. You use the sand as kind of a bulking agent to hold it where it needs to be, and then you just grind that flush. For bigger repairs, you can get into a variety of different things. That could be a concrete repair mortar, that could be an epoxy mortar. There's different urethanes for those purposes. Something that's a little stronger than the concrete itself, but also thick enough to allow it to be placed either horizontally, vertically, or overhead. You have different consistency materials for those applications. And then you also have to look at what kind of traffic is it going to have. It's going to have, forklift traffic. Is it going to be exposed maybe underwater, or are there any chemicals that are going to be coming in contact with it? So you wouldn't necessarily want to use like a concrete-based material where you're going to get into like salts or caustics, acids, things like that. You would go more towards a resinous material that's suitable for the chemical exposure that you have. The regular repair, or you're not going to have a lot of wheeled traffic on it, then you may not need to get into something in where a concrete product might work a little better. So it gives you the versatility to do what you need to do based on the application. But the biggest thing, like Josh was pointing out, is preparation, just like anything else. You want to think of it kind of like a chip in glass. Although you're going to fill that void, you don't want to miss the pieces your eye can't perceive and have those little broken clusters there. So you have to open that up and get rid of the loose stuff that would act like a broken rock and try and get down to something as close to being solid. It maybe still has a fracture, but its integrity is still there. Seal that all back together.
What products does Smith make that you would recommend for those applications?
For the finer applications, we have a product that was actually designed for bridge deck repairs, which is PCF 45. That's a fast cure polyurethane material, new component, very liquid. Think of it kind of like a water-like consistency. Very short working time, but it's designed to soak in and saturate and cure very quickly. And then you just grind that flush. Now that does have a very good chemical resistance to it as well. So it's suitable for use under virtually anything that you would put a traditional floor covering or coating system on top of, even overlays. So you can put cements over it, you can put a coating over it, you could even put carpet over it if you really wanted to. But it's going to be a lot stronger than the concrete itself when it's cured. So the likelihood of developing a new crack, not saying that there wouldn't be movement that could create a crack, but it's very unlikely that the repair itself would crack. The concrete's more likely to fail because it's weaker than the repair is.
Okay.
Something bigger, you may get into something like a polyflex, which is a polyurethane, thicker viscosity material, self-leveling. So that's for deeper fill repairs up to about 5 inches deep.
Josh, you have any experience with those products that you'd like to add?
Yeah, all three of them. When it comes to the PCF 45, I mean, it's a nice material because it hardens so quickly. You mix it with sand, or the sand is put down and then it's dumped into the sand because it's very, very thin, like water. And then the and the Polyflex, of course, I've used that as well to do spalls. But again, I mean, it's always a matter of what the manufacturer recommends as the product for that application. So I couldn't stress it enough that if I'm not sure the area that I'm repairing with a given material, I'd pick up the phone and call the manufacturer.
Well, that's a good segue into the next topic, spalling. We've all been on jobs where we've seen spalling in numerous places. Josh, again, from a mechanical perspective, how would you repair spalling to get the area ready for a chemical solution?
Well, a spall is similar to a crack in terms of we can only see the void that's there, but we can't really see how the damage took place. Therefore, we can't see what other effect there was as that damage occurred. So that means, again, going back to microcracking, we have to worry about not only the superficial material that's, let's say, coating the bottom of the spall, construction debris, wax, dirt, oil, whatever wants to fall into a void on the horizontal surface is going to fall there and stick. A grinder can't reach down into those. So our first goal is to get it clean. So whatever way that might be, with shot blasting probably being the primary way that I would do it. Could certainly do pressure washing, but in most cases, if I'm coating, I don't want to use water. So I can shot blast those spalls or nail pops pretty well and get them very clean. As far as the integrity of the bottom of that spall, so if we think of it like a pothole, at the bottom of that spall, I really need to verify that the bottom of it is not hollow or doesn't have more degraded material that even after blasting didn't come free. So in other words, I'd be pouring my material over the top of potentially loose material at the bottom of the hole. Yes, it's clean, but it's not structurally sound. So really the easiest way that can be identified, if that's a concern, I could just take the head of a hammer and drag it through there. If it's hollow, I'll hear that. If that's the case, then I would be getting into a chipping hammer. If it's small enough, just a handheld claw hammer, needle scaler. I just think of any way that I can get down into a minus imperfection and get it agitated enough to find within reason that the material no longer freely comes loose, then I'm content that I've got it as soundly prepared as I can. And again, the shot blasting as a final step before the coating is applied will get rid of any of the fine dust that was caused during that process, any remnant dirt, oil, or anything else that would be down there as a bond inhibitor. That's pretty much the best ways that I can think to prepare a minus imperfection, a spall or a nail pop.
Paul, what would be the next step from a chemical solution once it's prepared?
Well, once you have everything out of there, you need to determine, obviously, the depth. That comes into play because there's a lot of different types of products out there, and they don't all have the same capabilities. Some can be applied thick, some can't. So depending on what product's being used, as an example, the Polyflex, it's nice because it allows you to be a little more versatile. So it'll feather down. It's still self-leveling and liquid, but it has the capability to go from about 1/64 of an inch all the way up to 5 inches. So you could fill in these very irregular, uneven, kind of like a pothole, but small, irregularities in a floor and achieve something that is not only able to be ground, or shaved if it's a small enough spot. You could razor scrape it and shave the top loose before you do it, make it a little bit easier to grind in. But it also has the ability to withstand moisture and alkalinity from the substrate that may or may not be present. So you have to also take into consideration the exposure. Is this at the apron of a door to a residential garage? Maybe there's some salt damage that caused spalling. But you also have to look into how much salt got into that concrete, what exposure is going to be there in the future. If that gets water underneath it, because you just have the outlying section of the concrete that may or may not have any kind of caulking or joint material between the exterior slab or pavers or whatever it is, allowing water to get into that section, comes up underneath it. If that material can't handle moisture, freeze, thaw, whatever it may be, then the repair's not going to hold up. Where this will. It's designed for a multitude of applications. In many cases, it's overkill, but that's the advantage of having something that can allow you to do a larger magnitude of repairs and still turn it around quickly, accept traffic and other coatings on top of it. But you could certainly use, depending on the time available, you could use a concrete repair material or a patch, as long as it's appropriate for the type of system going over it, and other resinous coatings, epoxies, things like that. So you do have options, but the biggest thing is making sure that the product you're using is acceptable for the depth and what is going to go back on top of it. You definitely don't want to use something that maybe, although you could use like a, let's say like a construction grout or a repair mortar, that try and coat it the same day, that even though it may be fast enough for an overlay, it can't accept a resinous material because its strength's not there, and the percentage of water, because it hasn't hydrated that water into the cement matrix yet, all of a sudden you have an adhesion issue because you went on damp concrete that wouldn't have affected other concrete. So you have to be careful that you're using the right system based off of what its intended use is, the environment, and what's going to happen on top.
Brings up a great point. So you just basically stated that your products or some of your products will react differently to different concretes based on pH levels and other exposures to the concrete. What should a contractor do to kind of analyze the concrete to know what he's got before he chooses which product is best to put down? Are there tests that they can do to kind of protect themselves, or at least give them the best opportunity for the strongest adhesion?
There is some testing that you can do. The biggest thing that a lot of people miss is pH testing. That gives you an idea of what that concrete is exposed to and what you're dealing with. Concrete is an alkali material. It has to be. If you take the alkalinity away and you take too much moisture away, it goes back to its original state, which is basically sand and cement. But as a hard concrete material, you do want a certain amount of moisture there, and you do want a certain amount of alkalinity. Now, that's not to say that it can't get out of whack. If the alkalinity goes below a 9 or above a 12, you're running some risk of problems with the concrete. Now, it may be just a preparation and cleaning issue at that time to bring the pH back into balance because it was exposed to maybe too much road salt, like the apron example we were using. Or maybe something spilled on it. Battery acid in a battery charging area, for example. Somebody knocked over a bottle of bleach and it soaked in, or who knows what got into it, a contaminant of something, so forth. But it gives you at least a direction of a high and low that you're looking to stay within a realm. And if you're outside of that, it may be you need to have either a conversation with the manufacturer that supplies you with your repair products, or at least take a look at the systems that are going to be utilized there and investigate what the manufacturer states. I can only really speak for Smiths in this perspective, but we have on every system guide and every product data sheet what the products can and can't do, its limitations, and then what we also recommend for deep repairs, for crack repairs, for joint fillers, and what not to do in most cases. But at least gives you a direction and a guide of where to go. And again, like Josh has made the comment, when in doubt, call the manufacturer and get some advice.
So what I'm taking from that, though, is the contractor should always do a pH test just for no other reason to know what kind of moisture is in the slab and what he's working with.
Well, the pH is going to give you the alkalinity of it. It's not really telling you the moisture, but even if you don't have moisture, you can have a pH issue. pH isn't just coming from a moisture problem. It can be from contaminants. But the biggest thing that causes failure in concrete outside of moisture is contamination. So a pH test is very simple. It's just distilled water and a pH pen's the easiest way, but you can use, you know, an appropriate litmus paper or something. And it's going to give you a scaled result that kind of guides you in a direction. It is also utilized with moisture testing, specifically calcium chloride tests. But if you don't do that test and all you're checking is even moisture, you may be missing something because there could be a contaminant there that's the problem. And the moisture by itself is just another issue. So you're kind of forgetting something.
Thank you for joining us for part 1 in our discussion regarding concrete repair. To hear part 2 or other industry-related conversations, please subscribe to our YouTube channel and be notified when we post a new episode of Execs and Techs. If you prefer listening to podcasts, you can find us on Spotify, Overcast, Google Podcasts, or your favorite listening platform.